Alright, what's up everybody? I'm back today with another video, and in today's video we're going to do a nodal analysis problem. Alright, so this is going to be the first problem that we do a nodal analysis here, and our goal for this video is to solve for I naught. So this current that's coming down here, we're trying to solve for I naught, and we're going to try and solve that using nodal analysis. Alright, so let's get straight into the video to see how we can do that. So if we know anything about nodal analysis, we know that we have to label our nodes, right? So we have 4 or 5 nodes actually, right? So we have one here, 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 and then this is the bottom node. These two are the same, right? So let's label this our bottom one. Like we usually tend to label our bottom ones as our reference node, right? So let's go ahead and label this as a reference. And this will be our V1, V2, V3, and V4. All right, so here we have 4 nodes, right? So, or 5 nodes actually, including the reference. So let's look at how we can solve this problem. Now, a trick that we can do right off the bat is we see between V2 and V3, right? So if we have V2 over here and V3 over here, we see that there is a 6-volt charge in between these two, right? So there's a 6-volt charge in between these two. Now, whenever there's a charge in between 2 nodes that's not connected to the reference node. So for example, we can see that V1 is equal to 3 volts, and we know that because V1, the plus side is going here, but the negative side is connected to the reference node, right? It's connected to the bottom, like it's a straight path, right? We also know that V4 is equal to negative 3 volts, right? Because the negative side's here and the plus side's over here, and the plus side is connected to the reference node on the bottom, right? But V2 and V3, this negative 6 volts or positive 6 volts, depending on what side you're looking at it from, this 6 volts is connected to V2 node, right, over here, and it's connected to the V3 node over here. So it's not directly connected to the reference node, right? So over here we have that 6 volts is in between negative V2 and V3, right? Now, because the positive side is on V3, we can determine an easy equation, right? So right off the bat, because the positive side is on V3 and the negative side is on V2, we always do the positive minus the negative, right? The positive side always goes first, so we can do V3, right, minus V2 is equal to 6 volts, right? So we have one equation right here. V3 minus V2 equals 6 volts, right? So remember, if we have a charge in between 2 nodes, we always go from the positive minus the negative end, and then that is what equals to the actual charge, right? So V3 minus V2 is equal to 6 volts, right? That's the first step that you have to do. We have to find out our first equation to solve for I naught, right? So basically, if we go through what steps we need to take to find I naught, we need to find V3. There's no way we can find I naught without finding out V3 if we're using nodal analysis, right? So we have to find out 2 equations that have V3 in it, and then we can solve for what V3 is, and then using simple V equals I times R, our simple electronics equations, we can solve for what I naught is going down towards reference node, right? Okay, so now that we have our first equation, let's see if we can make other equations. So if we look at node number 1, we look at V1, let's look at what we have here. So we have, if we are going across, right, we know we have to do 2 voltages subtracting each other and then divided by the resistance, because if we're doing nodal analysis, we're basically doing V over R. So the difference in voltage, right? So the difference in voltage over reference or resistor actually is what gives us the current I, right? So we have to formulate a couple equations that can help us to do that, right? And before we try and figure out what our first equation can be, another trick we can do, right? So another trick that we can do, which makes this problem way easier, is that if we can see here between V2 and V3, right? So over here, between V2 and V3, we see that there's a negative 6 volt or positive 6 volt voltage source in between these 2 nodes, right? So because there's a voltage source in between these 2 nodes, we can do something called a supernode. So essentially, we can basically create a circle around these 2 nodes and combine these 2 nodes to make it one. So essentially, we can redraw this circuit. So we have V1 over here, then we have our supernode. Let's label this SN as supernode, right? Then we have our V4 over here, right? And essentially, we just have one coming down. So essentially, we have V1, our supernode, and V4 And then that is essentially how we would draw our circuit, right? So then if we look at this supernode, that is what we can do. So let's redraw this and see what we can do to make this equation easier to solve, right? So our V1, right, we have a positive 3 volts over here. So we can do 3 volts over here. Our V4 we know is negative 3 volts, as we talked about before. Now our supernode, we're trying to find current, right? So let's label the current that's going into the supernode from V1 is equal to I1, right? Then we have I2 going down here. Then we have I0 going down here. And we have I3 going over here. So as you can see here, we have 4 currents, right? But we're basically combining these 2 currents because of our supernode, right? So if we were to draw this over here, we can erase this, right? If we were to draw this over here, let's take a look. We have, if we come down here, this would be our I2, and then our I0 would be over here. Our I1 would come in, would come in, and then our I3 would go this way, right? So essentially what we did is we created a supernode. So we basically combined the I2 and I0 to come down the same pathway as we manipulated this circuit. And the reason why we were able to manipulate that is because there's a voltage source between V2 and V3, the 2 nodes. What we were able to do is create a supernode and combine these 2 currents together to make this equation easier to solve, right? So now, knowing that, let's see what we can do. So we know for the supernode, if we just erase this back to make it easier to understand, let's label this again. We have V1, V2, and V3, right? So let's go formulate an equation, right? So we know that to get I1, we know it's V1 minus V2 over, and we can see here that it's 6 kilo ohms, right? So we can put 6K, right? And if you're wondering why we're doing V1 minus V2, because we know that there's a positive 3 volts here, and we can assume that the current is going towards V2, right? So we're assuming that current is going in from V2 because the current in I0 is coming in a clockwise position, right? Because if I0 was going the other way and it was going up, then you would assume that current was going from V2 to V1. But because I0 is going downward, we're assuming that current is going in a clockwise position like so, right? So knowing that, we can assume that V1 minus V2 over 6K makes I1 come this way, right? So I1 is going to the right side. So we do V1 minus V2 is 6K, right? So we know that the current going in is equal to the current going out. So we're going to assume everything else is the current going out. So V1 minus V2 over 6K is equal to, right? And let's see what else we can do with the equation, right? So if we do our supernode, right? If we look at V2, if we have to find out the current going down here, what can we do, right? We know that V is equal to I times R. So then V over R is equal to I. Now we know that the reference node, the voltage here is always 0, and the voltage here is always 0 because it's a reference node, that there's no voltage on the reference node, right? So we know that the current I2, if we label this I2, we know that the current going down is V2 minus 0, because we start from the beginning minus the end, divided by the resistance in the middle, right? So we know that this is equal to V2 minus V0 divided by the resistance in the middle, and the resistance in the middle is 2K, right? Then what are we going to add this to? We know that the voltage also leaving the supernode, right? Because these 2 nodes are together, right? So we know V2 and V3 are the same node. So V2 and V3 are basically the same node. So we put I0 in the same reference over here, right? So I0's in the same reference going downwards, right? So V3 minus 0 divided by 6 kilo ohms. We can do the same thing once again, right? So we can do plus V3 minus VO over 6 kilo ohms, right? So VO is our reference node. So we do V3 minus VO over 6 kilo ohms, right? So now we have I2 and I3. Well, what about our equation for I3 over here, right? So we have I2 and I0. What about our equation for I3 over here? We have V3 over here, right? So we have V3 over here, and then we have V4, right? So what is I3? We have V3 minus V4 from positive and to the minus end, right? So whatever the current is coming from, that is where we start. So we do V3 minus V4 divided by 12 kilo ohms, right? To sign for what I3 is, right? So we do V3 minus V4 divided by 12 kilo ohms, right? So that is our final equation of what nodal analysis is for our supernode. So basically that's the nodal analysis for the supernode, right? So this is our equation, V1 minus V2 over 6K. So that's what I1 is. So this represents I1, right? Then we have V2 minus VO over 2K, which represents I2, V3 minus V0 over 6K, which represents I0, and then V3 minus V4 over 12K, which represents I3, right? So this is all our current in nodal form, right? So now what we're going to do is just plug in the values and let's see what we get. So we know that V1, we said before, V1 is equal to 3 volts because the positive side is connected to this node and it's also connected to the reference node. So we can say that V1 is equal to 3 volts, right? So we can write this as, using different colors, do 3 volts minus V2 over 6K is equal to V2. We don't know what that is, right? So V2 is still unknown to us, right? So V2 we still don't know, it doesn't have a real value, and V3 we still don't know, it doesn't have a real value. The only other voltage that we know is V4 because V4 is connected to a voltage source, and that voltage source is also directly connected to a reference node. V2 and V3 we are unknown to us because they're connected to each other as the voltage source is not directly connected to a reference node, right? So that's why we don't know what V2 and V3 are, right? So knowing that, we can write V2 over 2K, and the reason why I'm not adding the minus V0 is because it's 0. We know that the reference node is always going to be 0, right? So it's essentially V2 minus 0, so we don't need to add that, it's just a minus 0, right? So we're going to add it to here. Then we know that V3 is also unknown to us. We don't need to add the minus V0 because it's 0 volts. V0 is equal to 0 volts because it's the reference node, as we just said, right? Then we can divide this by 6K. Then I'm going to add this to V3 minus, and what's negative V4, right? So minus V4. V4 we said is negative 3 volts, so it's a minus negative 3 volts. That essentially just becomes plus 3 volts, right? So it's minus negative 3 volts over 12K. So just plugging in our values, right? So now what do? What we have to do is solve, right? We have to solve for a variable. And how do we do that? Well, if you guys remember, we made our first equation right off the bat, right? Remember this equation? V3 minus V2 is equal to 6 volts. So what do? We isolate, right? So if we see here, what do we know about this equation, right? We know to find I0, we said we need to know what V3 is equal to. So what is V3 equal to? V3 divided by 6 kilo ohms, right? So V3 minus 0 divided by 6 kilo ohms is what's going to give us I0, right? So we want to solve for V3. So how can we solve for V3? Well, if we isolate this equation, we have that V3 minus V2 is equal to 6 volts, right? That's our equation here. V3 minus V2 is equal to 6 volts. So if we want to isolate for V3, we have to make V3 by itself, right? So V3, or we have to solve for, so if we want to solve for V3, we have to make V2 by itself, right? So then we can replace V2 in terms of V3, so then we can solve for V3, right? So we can say that V2, essentially, V2, if we just rearrange this equation, V2 is equal to V3 minus 6 volts, right? So that's our equation. V2 is equal to V3 minus 6 volts. So now we have V2 is equal to V3 minus 6 volts. So we're basically going to replace V2, right? All the V2s, we're essentially going to replace it with V3 minus 6 volts, right? And that's what we're going to end up putting in our equation. So let's see what our final equation is going to be. We have 3 volts minus 6 volts plus V3 over 6K is equal to V3 minus 6 volts over 2K plus V3 over 6K plus V3 plus 3 volts over 12K. And then that is the equation we get, right? So essentially, with this equation, what we have to do is use algebraic formulas to solve for what V3 is equal to. So let's go ahead and do that. So if we just use simple fraction rules, let's divide this up. So what's 3 volts minus 6 volts? We get negative 3 volts over 6K plus V3 over 6K. So we keep the V3 over 6K because we don't necessarily know what that V3 is yet. And we're going to keep going. We're going to have V3 over 2K, and then we have minus 6 volts over 2K plus V3 over 6K plus V3 over 12K plus 3 volts over 12K, right? So then let's go ahead and solve this further. So we know that negative 3 divided by 6 is equal to negative 0.5. So we have negative 0.5 milliamps plus V3 over 6K is equal to V3 over 2K minus, then we have minus 6 volts over 2K, which is equal to negative 3 milliamps, right? So minus 3 milliamps because 6 divided by 2 is 3, plus V3 over 6K plus V3 over 12K, and then we have 3 divided by 12 is just 0.25 milliamps, right? So now we're going to simplify this even further. Let's see what we get. So if we bring all the like terms to one side, we see that we get V3 over 6K minus, so we're bringing everything over, minus V3 over 2K minus V3 over 6K minus V3 over 12K, and this is basically equal to, we're bringing the negative 0.5 milliamps, this part we're bringing it over, and we're bringing the over to the other side, so we have plus 0.5, so 0.5 milliamps minus 3 milliamps minus 0.25, plus 0.25 milliamps, right? So now we're going to isolate and simplify this even further. So let's change the color up a little bit for our last steps. So we know that V3 6K minus V3 over 6K, these cancel out, right? Because they're the same value. So left with basically negative V3 over 2K minus V3 over 12. So if we know anything about subtracting fractions, we just have to cross multiply, right? So when we cross multiply, we multiply the denominator, right? So we get 24 on the bottom. So we get 24K on the bottom, which is 12 times 2. Then we get 12 times V3 minus, right? 12 times V3, or 12 times negative V3, so it's negative 12 V3 minus, then we had 2K times V3, right? 2K times V3 is just 2K, so it's 2V3. And then this essentially, what it becomes is negative 12 V3 minus 2 V3. This becomes negative 14 V3 divided by 24K, right? And what is this equal to? We add all this up, 0.5 minus 3 plus 0.25. Then what we get is minus 2.25 milliamps, right? So now this is very easy as we have simple equation right here to solve for V3. So what's 24 times negative 2.5? We're going to bring this over. And then essentially what we get is negative 14 V3 is equal to negative 54, right? So we get negative 54 over here. Then to isolate for V3, what we get is V3 is equal to negative 54 divided by negative 14. And then essentially what we get is V3 is equal to 3.85 volts, right? So now we know what V3 is. So if we go all the way back to the beginning, we know that I naught is V3 minus 0 divided by 6K, right? That's where we're going to find out what I naught is. So if we go all the way back down here, we see that V3 minus 0 divided by 6K equals to I naught. And what is I naught equal to? That's essentially 3.85 volts divided by 6K is equal to 0.64 milliamps, right? So our final answer essentially is I naught is equal to 0.64 milliamps. And that is how you solve that problem using nodal analysis. I hope you guys enjoyed the video and understood. If you guys did, please make sure to like, comment, share, and subscribe. If you guys have any questions or concerns, please comment down below or email me at sharranacademy@gmail.com, and I'll make sure to get back to you as soon as possible. And if you guys like videos like this and want me to keep making videos like this, or any specific questions or topics that you guys have, please comment down below and I'll make sure to make the video on it as soon as possible. Alright, thanks guys for watching. I really appreciate it.